Everybody. We are going to start. Where is the mic? Is it working? Yeah. Hello. Hello. So we are done with the inflammatory process. Now the repair process has been started. So okay. So tissue repair is another important topic which you have to know about. And as acute and chronic inflammation stops, and as you know, chronic inflammation, we cannot give a true definition until we say that three things are there. Number one, inflammation. Number two, tissue damage. And number three, repair. So repair process usually starts in a chronic inflammation, but you have to have a knowledge of how this starts. So this is how we do repair if we do some surgical. So hi, you are taking attendance now?
No. Just sorry. Dr. Samah took the attendance. When you make your attendance, also make the attendance of Dr. Samah. Okay. And then please, every time, remind the doctor to take the attendance. So in order not to lose points.
You know that I usually take attendance in the middle of my lecture. So as I'll start, just remind me to take the Samah's lecture also. Okay. So the repair process, as you know, this is a surgical suture, and this is a very clean. If you do a clean surgery, after surgery you put this type of suture, and the process of repair start. This thing we will be discussing tomorrow. So, but today, you know that we have acute inflammation, then we have chronic inflammation, and then finally we have healing and regeneration process. Do you know what's the difference between healing and repair? Anybody? Healing and regeneration and repair. Yes.
So regeneration is when you bring the original cells back. Repair is when the cells change.
Yes. Yes, you. Regeneration is yes.
Adding to what he said, also regeneration only occurs in tissues that have living cells that can divide, while repair occurs in permanent.
Not stable cell, only labile cell.
Maybe stable.
Yes.
Granulation and adding new blood vessels.
So this will be repair or this will be regeneration. Regeneration. This is the other way. Okay. So we will be discussing this thing, the difference between regeneration and repair. In regeneration, there is no scar. But in repair process, at the end, you you see scar formation. So usually, as you people said, it's a proliferation or migration of specialized cells. And those cells, which are, as he mentioned, it could be labile cell or stable, right? They have a propensity of regenerating itself. So when there is a complete regeneration, and it depends how fast regeneration process of the cell is, then there will be no scar formation, right? The other one is a repair process in which where the regeneration cannot occur. We can take example of heart, myocardial infarction. The cardiac muscle is a permanent muscle and it will not regenerate. So the process of healing this process is by organization and progressive fibrosis and granulation tissue, as he has mentioned, right? So ultimately, at the end, we will be looking at scar formation. So it has, if we talk about tissue repair, it's a restoration of tissue architecture and function after the injury. Now, usually it has two ways. As we said, regeneration, when we have a capability of the cells around to develop itself, proliferate, or replacement by connective tissue or a scar. If these cells are not capable to regenerate itself, usually it happens in, involve both of the process. For example, if you have some problem in the skin, although the skin epithelium is highly proliferative, but in a chronic inflammation or long-term inflammation beneath the skin, or you have a big ulcer, so to repair that process, you had to have both of the process going on together, right? So it involves both the cell proliferation and interaction between the cell and cell matrix, extracellular matrix. So this we will be discussing later on. So this picture is very good to tell you how it goes. For example, this one is a totally renewal cells or labile cells like epidermis and GI tract epithelium or hematopoietic cells. These are the cells which are continuously being divided throughout the life. So they are always in a life cycle. We will discuss how it comes. Life cycle. So and if suppose even no trauma or no injury is taking place, you don't know, but your epithelium is shedding off. So a newly formed epithelium is slowly and gradually coming up in the epidermis from the basal membrane, from the basal cell, and it pushes the older cell out. So it is always been replaced by a new epithelium. So proliferative process is going on. So regeneration. Instead, these are stable cells. Stable cells are liver or kidney. So if you have, suppose if you cut half of the liver or half of the kidney or more than half, and the remainder area is still there, then they can develop itself on the other side, not on this side. Remember, if you cut from this side will never develop because there is no stem cell there. The remaining area, they have stem cell. So they start producing the organ which is been cut half. So it will divide on this side, not on that. Clear? The last one is, there are two. One is, for example, if you consider this thing as a heart muscle, they are permanent cells, they don't proliferate. So whatever happens, myocardial infarction, the tissue will be repaired by fibrosis. And in long-term chronic inflammation, you will damage the tissue so much that it ends up with fibrosis. So keep this picture in mind so that we will be discussing this. This is another good example. For example, what is this? Liver, and this is one lobule, and this is portal. Right. What is this in the center? Vein. Which one? And this one? Bile duct. This is hepatic artery. So, if suppose any injury take place, example is suppose hepatitis A. In hepatitis A, what happens? There is damage to the hepatic cells, hepatocytes. They injure. But in hepatitis A, the extracellular matrix remain at its place. That is not damaged. If the extracellular matrix or the architecture is maintained. So what happens once it is repaired, you will not find any difference between the uh, original one or normal one and after it has been repaired, because the extracellular matrix was not damaged. On the other side, for example, this liver is been infected by hepatitis B or some bacterial infection, abscess formation, whatever. So the architecture of the liver is destroyed. And when this liver will be repaired, although they have repaired some of the liver cells, but because of the architecture of the liver, the extracellular matrix of the liver, they are distorted. So probably you will see cirrhosis and fibrosis. Fibrosis of the liver is called cirrhosis. Clear? So you had to have extra. So this shows how important that extracellular matrix is. If the extracellular matrix is present at its place, nothing will happen. But if the extracellular matrix is lost, then you had it. So the repair process will be scar formation. Now, let's see what is in this lecture. Important background facts. Cellular proliferation, we discussed this. Growth factors is very important. One cell, if you want to proliferate, it has to be stimulated by growth factor, otherwise no proliferation. So there is a proliferation of single cell with single growth factor. Then extracellular matrix. So side by side, if there is a proliferation of the cells, you have to have a proliferation of extracellular matrix. Remember, extracellular matrix just acts like a cement. If you make a brick, so between the bricks you put cement. So join two bricks together. So this extracellular matrix actually a binding force, which has a very, very important function. You cannot develop without extracellular. So the process of tissue repair is regeneration and scarring, and it is treated, which we will be discussing tomorrow's lecture. And why won't go bad, this will also discuss tomorrow. So today, starting with the cell proliferation, lot of cell proliferation during this tissue repair. So we have injured tissue remnant, number one. Number two, vascular endothelial cells, they had to be developed, and fibroblast. It should come there, and they start secreting all the basic extracellular matrix are being secreted, are developed by fibroblast. Even some of the epithelial cells, they also contribute for majority of it. So we need to understand about stem cells, because if you don't have stem cells there, no proliferation. Proliferation capacity of different tissues. For example, labile cells, they are heavily proliferating. Stable cell, less. Permanent cell, no. Growth factors, very important. Cell cycle, yes, very important. Every cell has to go through this checkpoint, cell cycle. And finally, extracellular matrix, which we will discuss. Starting with the stem cells. So these are the stem cells present in different part of the body, and we'll show you which stem cell is present where, right? So if you have stem cells here, they will proliferate. For example, if there is injury, there is proliferation, and proliferation like deposit. Then suppose if you need 100 cells, probably stem cell has formed 150. Now this 150, they go into differentiation. Now by differentiation, the body has consumed only 120 cells. But what happens to the 30 cells? They will go apoptosis. They will die itself. You have done this topic, what is apoptosis, right? So we have divided tissue in three main groups. One is labile cells, which is continuously divided, which is the skin, gut epithelium, endothelium, bone marrow. The other one is stable cell, which is conditionally divided. If they need, they divide, otherwise, no division. Liver, pancreas, bone, renal tubules. And finally, we have permanent cells. Once they are produced, they will not reproduce again. They are called permanent cells. They are nerve, glomerular, cardiac, or skeletal, right? So once they are produced, they are never regenerated again. So they are always present in G0 phase. So continuous cells, the cells continuously proliferating all the time in the cycle, can easily regenerate after injury, contain pool of stem cells. So the stem cells are there near about. An example we have already discussed. Stable cell, again, cells that have a limited ability of the for proliferation and a limited ability for regeneration, except liver can regenerate very fast. Normally they are in G0 phase and can proliferate if injury. So they have propensity to come from G0 to G1. Example are liver, kidney, pancreas, and vegetal. The last one is permanent cells. Now these cells actually cannot proliferate. They proliferate in the intrauterine life, in the fetus. And once the fetus is born, the day it borns, full stop, right? Cannot regenerate. So injury always leads to scar formation, as in the first picture I showed you. Example are neurons, cardiac muscle, skeletal muscle. Now we have very important this cell cycle. You should understand what it is. Every cell has to pass through the cycle to give one cell. Has to pass. So this is continuous or labile cell, which is almost always present in the cycle. It almost never come out in G0. So it remains there, although the cycle will slow down or it can work fast if you need more. So they are continuously being divided. Continuous. So they are in a cycle. The stable cells are cushion cells like liver or kidney. They, after the baby is born, they come down in G0 here. Whenever they are needed, the proliferation, they come from G0 to G1 and they start moving in a cell cycle, right? And finally, we have permanent cells like neurons, cardiac muscle, or skeletal muscle. Once they come out in G0, they never enter into G1. So these are permanent cells. So we cannot have proliferation of these cells. So whenever there is damage to these cells, it has always been repaired by fibrosis or scarring. Let's discuss what is this cycle. It has two big checkpoints, here and here. This checkpoint is for DNA. It is called G1S checkpoint. So this is pre-synthetic and this is synthetic. So as G0 cell or this cell, which is almost going on, comes here, it has been stopped here. This is called restriction point. The cell stops here. Now we have policemen. You have traveled in by air, everybody probably. So if you pass through one area, stop, then they search everything. So they ask you to pass through a gate. And if something in your pocket starts, exactly the same situation here. They pass through this one, and if the DNA is damaged, start. Now, it doesn't mean that they will kick that cell out. They have a propensity that they will regenerate that damage. If the damage of DNA is very small and it can be repaired, then it can pass through this gate and goes into synthetic one. This is pre-synthetic. Now they have a clearance that you don't have anything. Now you can pass through. So DNA of the previous cell, which is going to be divided, it is now okay. It will go to the synthetic phase. Now the new DNA has been formed. If suppose there is a problem in DNA which is not been repaired, what will happen? The cell will be kicked off from the cycle and it goes to apoptosis and it will die itself. This is how you maintain the integrity of your body. You need everything clean. That's why no bad thing happens to you. If by mistake your machine is not working properly, although you have some pistol or something in your pocket and they allow you to go in, what will happen? Disaster. And anything can happen. This is what it's here. If the DNA is not right and they are not checking it properly, and this cell has passed from here to here, what will happen? Yes, start from this place. First chain, and then this cell again it passes again and again. Then this cell will convert into a cancer cell. Okay, so how to take this thing out? Can you show? Oh, okay.
Yeah, I'll take on this. Outside the box. Yeah. No, no.
So now the cell is in synthetic phase. A new DNA is being formed. And now in G2, which is pre-mitotic stage. So there is another checkpoint, is G2M, pre-mitotic to mitotic. The new DNA which has been prepared is checked again, whether they are formed correctly or there is something wrong here. If it is okay, then you get a signal, green signal, go, no problem. So this cell comes here and then division takes place. And as the cell divides, it will go out, a newly prepared one, and the original cell will go again in the cycle to form another one. And this cycle goes on like this. Is it clear? So if there is either this checkpoint or in this checkpoint, if there is a problem and it is not checked properly, what will happen? Dysplasia and cancer can happen. I think you are well aware. Remember, as I said, this.
From G2 out.
Yes, G2 and M. Again, we have a checkpoint here because in G2, a newly formed DNA is to be checked. That whatever new DNA, because now it's going to divide cell. So before division, they are checking in the newly formed DNA that either this DNA is also the same as the previous one or it is different. So if there is something different, again that shall go for a repair process. And if it is a minor repair and it is done, then repaired cell can go in the mitotic phase. Now it is ready for division and the cell is dividing, one cell, a new cell will come out. So this is how the whole process will go on again and again. Clear? Should we move now? Yes.
Why do we have a G1 test, but we don't have
This is also restriction. Yes. We stop here. Once it is a new DNA is formed, again we stop. And then we ask, show your document. And if your document is okay, then you will ask. Right? Nowadays, along with the document, they're asking for your vaccination. You have vaccination. Yes, then you go. Otherwise, you go back. This is what is going on. Okay, now it's done. Stem cells. How many types of stem cells? The stem cells are characterized by their self-renewal property. They regenerate again and again. Not like anything, but they need to have what? For dividing growth factor. Even it is self-renewal, they need to have growth factor. Otherwise, nobody will start. There are two main types: embryonic type or pluripotent stem cell or adult stem cell or somatic type, right? The embryonic type has propensity to make any cell you need. Heart muscles, skeletal muscles, neurons, liver, whatever you want, spleen, they can form anything. So they develop from the inner mass of the blastocyst, and it can develop in genetic or tissue of the body, whatever they want. Then they convert into multipotent cell. This has a limited property. So if you see adult cell, again, somatic cell, with a more restricted capacity. So this adult cell has propensity to form a specific type of cells, either endoderm, ectoderm, or mesoderm, right? They all have been studied in detail in the skin lining of the cornea, or particularly in hemopoietic system. So these are the cells which are always been forming again and again. So this picture shows here, this is a blastocyst. This is the inner part of blastocyst, right? Here, pluripotent cells are being formed, stem cells. So when the baby is in the uterus, intrauterine, these cells are forming everything: hepatocyte, neurons, cardiac muscles, hemopoietic cells, pancreatic cells, whatever they want. And then after 9 months, the whole baby is ready. Now this pluripotent cell turn into multiple cells. So when the baby is born, there is no further pluripotent. It's multipotent, and then they are in a differentiated cells like ectoderm, endoderm, and mesoderm. So they will only form these cells. They cannot switch to one another. Okay. So now this is skin, and they have seen that these somatic or adult stem cells are present in the base, just basal cells, just near the basal cells, right? And they start proliferating and go up till the top. And what will happen? The top layer shades off regularly. You don't even remember, and you can see, but it is going on regularly. It is also present in a bulge of this hair follicle, so your hair are also being formed regularly. If there is a problem in this stem cells, somebody who has less amount of hair, and some of them are richly incorporated with hair, and like me, becoming older, so the hairs are shedding off probably less amount of oil. In GI, just above this Bennett cell, we have stem cells, and these stem cells has propensity to form enteroendocrine cells or absorptive cell, goblet cell, whatever. All GI tract cells are formed by these stem cells. We have here, so that we have no problem. They are continuously being formed. Or we have in liver. This is actually HLE, which shows this is basically are the whole cells, which are dividing cells. Here, this is a central canal, right? This is basically a duct. So actually, this duct, by duct is this is called canal of hearing, right? If you remember your liver histology, this is canal of hearing, and you all know that these hepatocytes are continuously forming bile. So the bile is, this is one side, this is another one. So there must be one canal of hearing here, right? So they have only taken this one. So just after the in this side, these are all stem cells of the liver. So they are continuously being forming hepatocytes, right? So their presence is near this canal of hearing. And this is actually cornea. So it's just near the limbus where this cornea ends. So there are a number of stem cells which are continuously being formed. And thanks to God that you even don't remember or know that your cornea is always being replaced. A new cornea is formed, and alhamdulillah, you can see each and everything clear. Clear? Okay. Important points. Growth factor is very important. One cell divide with one growth factor. If no growth factor, no division. Remember. So action is they stimulate cell division and proliferation. They promote cell survival. Growth factor. So there are multiple growth factors, and growth factors are seen by GF, growth factor, fibroblastic, epidermal growth factor, transorbit growth factor, platelet-derived growth factor. So there are many growth factors, and some of them I have listed them there. And you don't have to remember all of them, but at least what I have shown you in that list, you should know. Okay. So this is a list of growth factors. I want to remember at least this both, this one and this one. This is first and this is second. So epidermal growth factor, transforming growth factor alpha, hepatocyte growth factor, vascular endothelial growth factor. So this growth factor also show what they are doing and which cells are being secreting. So I'm not going to repeat all those. So you just see it. And the important thing is angiogenesis. For example, VEGF is one of the growth factor which cause angiogenesis, right? And for example, keratinocyte. So epidermal growth factor, they usually form keratinocyte. So this is probably we can ask in your exam that which growth factor is forming which type of VEGF. This is another one. For example, here there are two fibroblast growth factors. One which is acidic and two is basic. Basically, this basic fibroblast growth factor, they form angiogenesis. So this, or they can even form fibroblast, as the name says. This platelet-derived growth factor, they are not only chemotatrid for neutrophil, but they are also forming or proliferating fibroblast endothelial cells and synthesizing extracellular factors. So on. So you please kindly remember these two tables. See it and remember it by heart. Clear? Then we have different functions of this protein. Number one, it's called autocrine. The cell is secreting and it is acting on itself. For example, cytokines are interleukin 2. You remember, we were discussing in chronic inflammation. The interleukin 2 secreted by lymphocyte and it is acting on the same lymphocyte to produce more lymphocyte. So this is called autocrine, acting on its own receptors. Receptors are there. Then we have paracrine. Whatever growth factors are being secreted, it is acting on the nearby cells. For example, lymphocyte, they secrete tumor necrosis factor. And they stimulate to form more and more macrophages. Allow to come out. It's just an example. So this is lymphocyte stimulating macrophage, or lymphocyte, they are stimulating fibroblast, but they are near to each other. The third one is endocrine. Growth factors travel from here by the blood vessel and go to the distant side. The example is human necrosis factor and interleukin 1. Produce somewhere else, go to the hypothalamus, through blood vessel, and what it does? Temperature, pain, right? So these are the things. They are acting as a endocrine. Secreted at one place and acting on a distance. Clear? I think we go for your attendance first. Okay, please. Hello, come back. Come back. Yes, I think it is working. When you keep quiet, you will listen very well. So we have discussed this thing. What is autocrine, paracrine, and endocrine? Finally, we have some ligands for this process. Receptor with the intrinsic tyrosine kinase activity, one receptor, which is this one, right? This one. Then we have G protein couple 7 transmembrane receptor, which is this one. And the third one is receptor without intrinsic enzymatic activity, which is this one, right? So we have 3 receptors in which the first receptor, which is intrinsic tyrosine kinase activity 1, all the growth factors usually go and attach to this one. And once it is attached, there are 2 different processes. One is PLC gamma and the other one is PI3 kinase. By this, they start and then reaches up to the transcription factor activation. So these are the pathways. For example, PI3 can kinase pathway by AKT, they activate this one. MAP kinase pathway by RAS-RAF, right? And then by MAP kinase phosphorylation, they activate this transcription factor. IP3 by the release of calcium, they activate this one. This is for the first one. The other one is, sorry, G protein couple. So multiple inflammatory mediators, hormone, and all chemokines, also pharmaceutical drugs. They usually take this receptor. Dr. Dilip Arora or Dr. Sama, they must have taught you. All the drugs usually use this receptor and they go in cyclic AMP pathway and then they activate whatever they want to make changes. And the last one is receptor without intrinsic enzymatic one. So many cytokines, including interferon, growth hormone, CSF, EPO, which is erythropoietin, they actually take the last one and they take this JAK-STAT pathway, and then they convert or activate this one. Is it clear? So you should remember there are 3 receptors and how these growth hormones, the cytokines are different things can take receptors. So you should know which receptor is taking which thing. Right? These guys go through this path. Now, one thing for this really important, so we have kept it separately, which is RAS1. Usually the tumor starts from, so they have kept it different. This is the same growth factor library, right? And this is the same RAS, but in a modified, enlarged. So you can see. So as the growth factor comes here, they stimulate this bridging protein, which is GRB2 SOS. This is in an inactivated form, converts into RAS GTP, which is one activated one, which is controlled by GAP. Once it becomes activated, then the MAP kinase cascade starts from RAF to MAC to ERG. Finally, it again causes activation of this transcription factor. This is a normal type of thing. For example, one growth hormone, whatever growth factor come and attach here, it stimulates this thing, and then finally transcription goes in. But in neoplasia, probably Dr. Oban is going to teach you after a while, 2 weeks after. This RAS, there is mutation in the gene, so it does not wait for growth factor. It becomes self-limiting, and they start moving like, and more proliferation starts going on, and then a neoplastic process. Clear? Clear, everybody? Yes. Clear. Okay. Now let's go to extracellular matrix, which are really important. As I said, they are the things which construct the building. For making a building, you must have seen columns and beams first, and then you put the bricks in between. The main structure is by beams and columns, and this is what they are doing. 2 forms. One is interstitial matrix, and the other one is basement matrix. So they are forming a pillar as well as cement, right, to hold the body. If you are standing like this, remember, it is by extracellular matrix. If you just proliferate the cell, epithelial cell, you will make a ball without any shape. But this extracellular matrix is actually giving you a shape of this body. Is it clear now? Okay. So we have 2 important types. So they have a lot of things to do. Number 1, sequestration. They sequester water and mineral. They grab those things, give cell scaffold a shape, and store growth factor. So what growth factor is forming, they usually hold it, and whenever the cell need, it gives. So you don't have to wait for a long because they are already holding those things with them. So if you talk about the interstitial one, the first one, it is the form of extracellular matrix present in the space between the cells. So they are actually working like a cement, as I said, between two bricks, cement, so that they can hold it properly. In a connective tissue between the epithelium and a supportive vascular. So vessels are being supported, epithelium is being supported, so they are working extensively. Synthesizes by fibroblasts, which is a type of cell, and the major type is fibrillar or non-fibrillar collagens. These are collagens. Along with this, we have fibronectin, elastin, protoglycans, hyaluronate, and other elements. So if you see, I'll show you the picture at the end. Yes.
This doesn't include the cell's glycogen, right?
Yes?
This doesn't include the cellular glycogen.
No, no. So this is extracellular. So basement membrane, again, this is a specialized type, organized one, around the endothelial cells and epithelial cells, right? So because it is beneath the epithelium and supporting the overlying epithelium, they are chicken wire-like appearance, and they are formed by amorphous non-fibrillary type 4 collagen. So this is a picture in which both of the interstitial and basement membrane is shown. The red color is the basement membrane here at this one. This basement membrane is holding not only epithelium but also endothelium, right? And they are forming a good structure of a vessel around it. The epithelium, which is based on this basement membrane, it is basically dividing this structure with the above one. So important. Then this is actually interstitial matrix. So this is filling up the gaps. Epithelium and blood vessel, so they are here. And what they are doing? They are producing a gap between these so that it is not going to touch this. It is not going to touch the muscles. So these matrices are formed and forming a good structure. Clear? Okay. So they have different structures. So I am not going to go deep in detail, and neither I will be asking this nitty-gritty, very small thing. But you should know that they have different structure, and they are being formed by fibroblasts down and some epithelial cells up. Clear? Now, function of the extracellular matrix. They have several important. Number one, it provides mechanical support to the tissue. Collagen and elastin. It acts as a substrate for the cell growth, as I said, the whole growth factor, and when the epithelium is needed, it goes up. Formation of the tissue microenvironment, for example, if it is there in the blood vessel, so they are forming a good structure of a blood vessel, forming epithelial layers so that the whole GI epithelium is based on this basement membrane. So it holds the epithelium tightly, and when it breaks down and epithelium goes down, what you call that? You call it cancer. Because of this basement membrane, if it breaks down and the epithelium goes down, then we call it a dysplastic process. It should not come down, right? So this has a very important one. And it regulates all the proliferation and differentiation. How much proliferation you need and how much differentiation you need. For example, here you need stratified squamous epithelium. In GI you need columnar epithelium. In urine tract you need transitional epithelium. So this differentiation they are maintained by this extracellular matrix. So an intact extracellular matrix is required for the tissue regeneration, and if the extracellular matrix is damaged, repair can be accomplished by only scar. So just remember my first picture of liver, where the basement membrane or this extracellular matrix were disturbed, cirrhosis of liver.
when you get the wound injury in the skin, it destroys the examination. That's why it's starting to hurt the skin.
Yes, because of that. So extracellular matrix is multiplying force.
And it's damaged.
So you had to have a perfectly right extracellular matrix to keep the body in a shape. Thank you very much, Dr. Garvin. So I'm just done with my lecture. We have taken my attendance. You can hold. So tomorrow,
Stop sharing. Rati, stop sharing.
8 to 9, 9 to 10.